Hello, everybody. Welcome back. Robbie here with you. So today we're going to talk about thermostatic expansion valves. Sounds good. We have a lot to learn today. And it's going to be a little bit long, but hopefully not as long as the compressors I did. Okay, share screen and slideshow from current slide. Okay, on the menu today, I open a restaurant. All right, the restaurant is called Metering Device. Chef, I am Executive Chef Robbie. Okay, on the menu, appetizers, refuel refrigeration system, the pre-meal fixed metering device, the main dish, thermostatic expansion valve. I'm going to talk a lot about the thermostatic, the balanced port, excuse me, that's misspelling, type of TXVs for different application, adjusted TXV, and a story I have, and we have a TXV quiz. Then for dessert, electronic expansion valve. I try to make it quick, but I can talk about TXV forever. Alrighty, first we gotta do review refrigeration system. Okay, there's the one I made from before. I'm sure you've seen this if you've seen my previous videos. We're gonna split it in fours. Alrighty, and we have the split in four. The vapor side is the top, and the liquid side at the bottom. Then we have the low side on the left and the high side on the right. Okay, so evaporator. Evaporator is the heat absorber and low side. Then compressor is a temperature and pressure increaser. Condenser, the heat remover. Okay, and the high side. Now, today is about TXVs. Metering device or TXV, or expansion device. Temperature pressure decreaser. Alrighty. So system is off. All right, Freon in liquid form. All right, liquid form. Then compressor comes on and creates a lower pressure, creates a lower vacuum, lower pressure. Freon begins to boil and reach boiling point, and that's your latent heat. And there we go. Now it is boiling, liquid vapor mix. And by the end of the evaporator, it should be 100% vapor back to the compressor. Alrighty, on the high side, compressor will create a higher pressure. 100% vapor comes out. First, we de-superheat. Freon begins to condense, de-superheat, then condense. And when it's condensing, it's called latent heat. And now we're on liquid vapor mix. Then next, we'll turn into 100% liquid towards the end of the condenser. Then we have the metering device, like spraying in a bottle. 100% liquid in, 75-25 out. Freon expands in the metering device, 80-20, 75-25. Okay, and that's what we're gonna talk about today. And then it comes out boil liquid vapor mix. Okay. A metering device similar to the freeway ramp. Regulates the flow of cars. Right, metering device regulates the flow of liquid refrigerant from high to low. And the metering device regulates the flow of cars from the ramp to the freeway. We have sensors and metering lights. Okay. System, evaporator, suction line, compressor, condenser, discharge line. Condenser, compressor, discharge line, then condenser, liquid line, metering device, goes on in metering device, expansion line, evaporator, goes on in circles, and circles we go. All right, now metering device, Sporlan, Parker bought Sporlan, and Danfoss is the two big things. First, do yourself a favor and create a free account with Danfoss Learning. I did. Welcome, Thomas Learning. I did the expansion valve test study. I knew everything. I just review, and I did a test, and class in progress. It's a good learning. Only a fool will refuse free education. All right, so go to After this class, go to Copeland, Danfoss. Alrighty. Metering device. We have the cap tube, orifice, thermostatic, automatic, and electronic expansion valves. And we have fixed and the fixed orifice and the fixed metering device and the adjustable metering device. All right, metering device, also called expansion device. It is the brain of the system. Alrighty. We have 5 types: thermostatic expansion valve, electronic expansion valve, automatic expansion valve. These are adjustable. We also have the fixed, non-adjustable, the capillary tube, and the orifice. The metering device is the pressure reducer located between condenser and evaporator. All right, the metering device expands the liquid refrigerant. Same as spray bottle. When liquid gets expanded, it will flash liquid vapor mix and will drop in temperature. Water drops in temperature when sprayed and flashes. As water going to tiny droplets, blah, 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 rapidly evaporates and cools down. You can Google the physics. All right, and then we have a piston metering device, which is also the orifice. Sometimes they call it piston, sometimes they call it orifice. A subcooled liquid from the condenser comes in and out flash gas. Subcooled liquid, flash gas, just like spray bottle 80-20 mix. The metering device regulates the flow of refrigerant to the evaporator. Same as the metering lights regulate the flow of cars onto the highway. 100% liquid enters the metering device and 80-20 liquid vapor mix leaves the metering device. All right, traffic without metering light. Traffic on major highways. The metering system has sensors, lights to monitor traffic, regulates the flow of cars, sensors, and lights. TXV and thermostatic and electronic valves have sensors to monitor the temperature and pressures to regulate the flow of refrigerant into the evaporator. Same thing, as they have sensors, monitor the pressure and temperature and regulate the flow of refrigerant. First freeway ramp was 1963 in Chicago. Fun fact. Okay. The sensors control the lights. And adjust red for capacity control. More cars equals more reds. Equals less flow. More cars on the highway, more red, less flow into the highway regulates the flow. TXV and electronic expansion valve, self-adjusting. Sensors control the valve. If temperature or pressure increases, the valve will open and add more refrigerant into the evaporator. Temperature, pressure increase equals open and more refrigerant. Automatic expansion, the automatic expansion valves are kind of, you can say manual adjustment. We have to adjust them ourselves instead of automatic, man or woman. And the cap tube and orifice are non-adjustable. Okay, now a stop sign regulates the flow of cars. 1 car per stop, same flow, non-adjustable. And that's your cap tube and orifice, non-adjustable, just a stop sign. Okay, next. There are fixed metering devices. Same flow. The automatic expansion valve, manual adjustment. You can adjust it 1 time and leave it. Like a person holding a stop sign. Sometimes stop, sometimes no stop. But you can adjust it. A qualified service technician needs to adjust the boiling point on the evaporator using PT chart. I will cover that later. Alrighty, cap tube and orifice. Cap tube and orifice. View of a cap tube and a view of an orifice. Just like water, the longer the hose, the less pressure, right? Longer the hose, the less pressure drop. Next slide. My mouse is stuck. Next slide. Okay. Oh. Okay. We have a long hose, water pressure decreases, long hose, less pressure. We have a shorter hose, the water pressure increases. Shorter hose, more pressure. we have a very long hose, then the water will increase dramatically. Very short hose. We have a very short hose, the water will increase dramatically. Very short hose, a lot more pressure. Similar to TXV. The TXV, long, normal, or small, will affect the low pressure. Now, normal evaporating temperature degree. That's the boiling point, evaporating temperature. Means the boiling point or saturation temperature or the dew point or the midpoint. They all means pretty much the same thing. You can use all these terms. That don't mean the same thing, but you can use any of these terms. All these works. All these are the saturation point in the system. I'll explain. Evaporating temperature, the temperature at which the freon boils inside the evaporator. That's your evaporating temperature. That's your evaporating temperature everywhere in the liquid vapor mix line. The boiling point, the specific temperature where liquid refrigerant rapidly changes to vapor. That's when the boiling point starts. The boiling point is the start of the evaporation temperature. The dew point is the last drop of the liquid refrigerant when it becomes 100% vapor, which is at the end of the evaporation temperature. And then saturation temperature, somewhere in there. Now, the midpoint, that's for blend. When the refrigerant boils over temperature change called the glide. The midpoint is the phase change. So the midpoint is the middle point between gas A and gas B. Remember, gas A plus gas B, the midpoint is vapor AB. Okay, if it makes sense. So the midpoint for blends. Now, saturation temperature is the exact point where the refrigerant boils from liquid to vapor in the evaporator or in the condenser, the high side from vapor to liquid. They're both called saturation. That's why I don't like to use that word, too confusing. Let's just use boiling point for the low side, condensing temperature for the high side. Saturation is for both. So let's just not use it at all. But it's also saturation temperature is correct. All right, so that's your saturation temperature inside the point. And now the bubble point, that's for the high side. The bubble for the high side. So now we're gonna go PT chart. We have pure refrigerant non-blend R22 and 134A. And we have, for example, R404 is a blend. That's why you see bubble and dew. Okay, and that's your blends. You see bubble and dew for the blends. Now, the bubble, think of the bubble in the side glass on a liquid line of the high side. And the dew, think of the Mountain Dew soda, cold, low side. And there's your bubble in the high side is high side, and soda, Mountain Dew, low side. That's how we know bubble and dew, easy to remember. Okay, I hope this is good, interesting, but something's wrong with the slide. Okay, so freezer, -10. Now, freezers, -10. That's your boiling point, right? The evaporator should be, boiling point should be 10 degrees below box temperature, right? Think about it. Look at the small screen now, guys. The high temperature moves to cold temperature, right? So we need the evaporator here colder than the room temperature to go in, right? So now, that's for freezer, huh? Low temp. So the evaporator temperature, right, should be at least 0 to -10 boiling point, because 0 degree freezer temperature, we need to go in it. So it's gotta be colder boiling temperature. So for freezers, boiling temperature -10. For refrigeration, the boiling should be about 15. And refrigeration boiling temperature about 20. Why? About 20 below box temperature. 35 minus 20 equals 15. And for air conditioning, the boiling point should be about 35. AC, the high temp, considered boiling point should be about 40 degrees below room temperature. Room temperature 75 minus 40, 35 degree boiling point. Okay, I hope this makes sense a little bit. We'll cover it again later. Okay, but something's wrong with this. Something's wrong with my slide. Something's wrong with this one. What's wrong with my pressure enthalpy chart? No superheat and no subcooling. This is the proper chart. And since we're here, let's cover it. Boiling point, dew point. Okay, this is nothing. Okay, now we start with the low pressure vapor mix, number 6. That's your boiling point. Cold, low pressure liquid. Then, I skipped too much. Number 7, 100% vapor, right? That should be the dew point, right? Yep, dew point. Number 1, superheated vapor. Okay, now why? Because between number 7 and number 1, we have temperature increase. That's your superheated vapor. That's your superheat, 8 to 12. Okay, now compressor between 1 and 2, high pressure vapor. In the condenser, first we do superheat. Number 3, beginning of condensation. I guess you could call that a bubble, I guess, from beautiful side, correct. And number 4, end of condensation. And number 5, subcooling. Okay. And subcooling number 5. And we have, of course, high pressure. It's not hot anymore now. Now the temperature is warm, high pressure liquid in. Okay. Enthalpy is the heat travel into cool evaporator, cold that occupies space. Okay, never mind that one. Heat in, heat travels into cool, condenser colder than the outside air, and heat out. All right, now let's go back to the capillary tube. Alrighty, so on this chart, this is how to size it. This is all right. So we gotta know the horsepower in the refrigerant. Quarter horse, example, quarter horse R22. We need for low temp, we need 12 feet of size TC36 and 6 feet of size T36 for medium temp. Okay, makes sense there. As you can see, freezer longer, lower, more pressure drop. Cooler, same exact diameter cap tube, longer, less pressure, shorter, less pressure drop, because evaporator for the freezer runs colder than evaporator for cooler. Example number 2, R12, 6 horsepower, that's a small one, 12 feet for cooler, but 8 feet for AC. Okay. Now, next, the note, static versus forced air. That's your static evaporator, no fan. Static equals no fan. Forced air equals forced fan. Alrighty. We have 3 cap tubes, diameter. Can all 3 do the exact same job? Yes, sir, ma'am. Longer, medium size, and short. The smaller diameter, the longer the cap tube. The larger the diameter, the shorter the cap tube. The diameter and the lengths affect pressure drop. Example, for a quarter horse R12, medium temp. So boiling point should be about 15, 20 medium temp, correct? Yep. Factory, 0.04 inch ID, 90 inch long. We can use 0.52 ID and 60 inch long already, because the chart will tell us. All right, these are tools for the cap tube. Cap tube sizing, exactly. The cap tube depends on the length as well as diameter. Changing the diameter between and ID can double the flow. The longer the tube, the slower the flow. The shorter the tube, the faster the flow. All right, this is made by JB. JB chart have size cap tubes. Follow the example 3rd. Alrighty, now if we have easy to fix, we have a leak. Look at that. Easy to fix. Some video online I found. I did that many times in my life. But sometimes not too easy to fix. All right, now orifice piston. The orifice or piston. It's a fixed size medium device that restricts the flow of refrigerant, drop in pressure, temperature as it enters the evaporator. Same as a cap tube. All right, so the example in a heat pump system, AC mode. Has your piston liquid in, free flow, liquid line in, nothing happens. Now, heat pump mode, liquid in, the piston, restricted, heat pump mode, and expansion. All right, so in AC mode, piston doesn't do anything. All right, it's just regular liquid line. But in heat pump mode, it becomes the metering device, expansion. Alrighty, let's move now to the automatic. No more cap tube and piston, and not much now. Automatic expansion valves. Many applications for the automatic, but mostly for small stuff. We have most of them for ice cream, slush machines, hot gas bypass, that's freezers. Some are for PTAX, personal terminal, package terminal air conditioner, or package terminal heat pumps. And some for vending machines and ice machines, okay? And some are used for hot gas bypass, have nothing to do with metering device. All right, but most of them are used for liquid injection, which is metering device. All right, automatic expansion valve. We have the strainer. Liquid goes in, we have a strainer. We have the valve and the seat, the valve, and liquid refrigerant goes out, liquid vapor mix. And the control spring on top. Okay, so now, if we adjust it down, it's going to open and let more refrigerant in. So we can adjust it manually and leave it. More flow, the higher saturation temperature, pressure, higher boiling point. All right, now PT chart. Medium temp, R30, medium temp, 35-degree temperature. Boiling point should be about 20 degrees below. 35 minus 20, we need 15-degree boiling point. Sounds right. R134 is easy. 15 pressure equals 15 temperature equals 15 pressure. Freezer 0 degrees. So I set my automatic expansion valve until my pressure is 15 and forget about it. We're good to go. Freezer 0 degree low temp. Boiling point about 10 degrees below box temperature. 0 minus 10 equals negative 10 boiling point. Saturation temperature, whatever you want to call it. Okay, so negative 10 equals 24 psig. I set my pressure control at 34 psig. I don't have to worry about it. Okay, and you adjust it up and down as pressure. I guess think about it now. We adjust it down, right? It would let more pressure in. Pressure should go up. You adjust it up, then it should restrict and pressure should go down. Okay, and it's very common for air conditioning, 35 degree, but you're not going to see automatic expansion valve on air conditioner, though. A bad example. Saturation temperature on a small chest freezer, evaporator between negative 10 to negative 20, correct? Small juice dispenser, 28 to 35. Beverage going to be between 38 to 42. Okay, so now for air conditioning, which is just in theory, in reality, you're not going to see automatic expansion valve on air conditioner. Well, we could, but it doesn't make sense. You put a cap tube on it, it's cheaper. It's not really needed, but anyway. So 35 degrees, it should be about adjusted to 24 PSI. That's not right. Something's wrong here. It should be 62 PSI. It's a misprint, excuse me. Okay, small saturation temperature. I didn't finish this one. All right, well, negative 10, it should be about, what is it, 404? I don't have it. You get the picture. All right, now move on to the fun stuff, thermostatic expansion valve. Okay, here we go. Coupled liquid, like spring in a bottle. Alrighty. So the oil is mostly in the compressor and everywhere. The low pressure gas, end of the evaporator and the compressor. Saturated low pressure gas exiting the expansion valve and in the evaporator. The high pressure liquid in the condenser entering the TXV. Okay, non-condensables should never. All right, now, and the high pressure gas discharge line beginning of the condenser. All righty, evaporator, close side, evaporator, expansion, thermostatic expansion valve, low pressure gas, saturated low pressure gas. Okay, and high pressure liquid enters the metering device. 25% liquid vapor mix, or 80-20. Freon starts to flash liquid, ends 100% vapor. The XV made out of the body and spring is inside. Spring is inside. And we have the diaphragm, also called head. And the diaphragm, transmission tube, and the sensing bulb. That's part of the head. So the head is the diaphragm, transmission tube, and the sensing bulb. There's your sensing bulb right there. The XV controls pressure and temperature in the evaporator. Technically, only controls pressure, because temperature, it varies when you open the door. Temperature changes. Technically, the proper way is controls only pressure. Alrighty. So now, when we have low pressure, when the pressure decreases, the XV will close. Suction line temperature will affect the diaphragm. Suction line temperature increases, temperature will go up. The XV will open. All right. Spring is set 8 to 12. I'll cover it more later. As temperature drops, diaphragm pressure will drop. Valve will close. As temperature rises, diaphragm pressure will rise. Valve will open. Okay. Another example. This one from the Denfos learning I talked about earlier. The pressure inside the bulb decreases. Diaphragm move up. The degree of opening of the valve decreases. Less freon flow into the evaporator. All right, now let's talk about the standard TXV. If orifice goes up, if orifice goes down, more flow. If orifice goes up, less flow. Now let's go about thermostatic expansion valve. The pressure P1 plus P4 equals P2 plus P3. All right, first, P1 is the pressure of the bulb, okay? And that's the opening force, push down to open. Pressure number 2 is the evaporator pressure. Okay, that's your closing force. Pressure number 3 is also closing force, your superheat spring pressure. And the opening force is condenser pressure, liquid pressure from the condenser, high side pressure. That's your opening force. Alrighty, there they are. There's a video TXV operation. And now let's talk about standard TXV versus balanced port TXV. We have high inlet pressure opens the valve. Too much refrigerant flooding. High inlet pressure opens the valve. The piston rise and push against the diaphragm. It's a balanced port. Feeds the evaporator properly. So instead of having open force, open, close, and close, now we only have 3: open, close, and close. We eliminated the high side. For places where temperature varies a lot, will affect the expansion valve when the pressure in the high side changes. That's one reason why they have them. Another reason is I'll explain here in a little bit. Next slide. Balanced ports have a wide range. For example, AA capacity is good for 1/8 to 1/3 for R12. The B capacity is good for FAFO2, 1 1/4 to 2 horse. While the standard there, AA size is good for 1 1/3 and BB side 1/4 and 1/3. While the standard TXV only have one side, that's it. This valve only two tonnage. This one is only half a ton. This is C for cooler. GC, I'm not sure what GC is. Only one size per valve. That's why. So I like the balanced port. When I do service, I have it in my truck in case I have something's wrong with the TXV, then boom, I have it in the truck ready to go. All right, now we have sweat, the brazing type, internal equalizer versus flare and external equalizer. Sweat versus flare, internal versus external. So the connection, suction, liquid line, and expansion line. The one on the left is sweat, is flare nuts, and the other one is sweat, you brace it in. And okay, and the adjustment at the bottom. But the one, this one have external equalizer. Alrighty, we're gonna talk about that, very important. External equalizer okay, so that one is external equalizer sweat connection and internal equalizer flare connection. Now, single circuit evaporator versus multi-circuit evaporator. Single circuit, only one way in, one way out. Single circuit evaporator, one way in, one way out. Multi-circuit evaporator, as you can see, we have 6 ways out and 6 ways in. Small evaporator have only one way in, one way out. Single circuit evaporator, we can use thermostatic, internal equalizer, a cap tube, an electronic, an automatic, a piston, I guess, but we cannot use external equalizer. Will not work. Alrighty, now liquid line in, TXV, expansion line and distributor, 6 in, suction line, 6 out. All right, now with the transmission line, sensing bulb, transmission lines, sometimes they also call it the cap tube, the equalizer line to read the pressure of the end of the evaporator. Equalizer measures the pressure at the end of the multi-circuit evaporator for the TXV. The transmission line, also called the cap tube because it's a small pipe, but it's not the cap tube used as a metering device. This cap tube is not the transmission line. Students get confused. Robbie, this is the cap tube. No, that's a transmission line, man. So it's confusing. I apologize. So many things in HVAC. Okay. And we have here 6 in and 6 out. Okay. Now let's break apart the expansion valve. Liquid in, liquid out. There's the body, the thermostatic element or the head and push rods. This is the external equalizer connection. Now all the stuff go inside the body. We have and this picture of the valve and the push rod. We have the seat and the pin carrier, superheat spring and spring guide, and the bottom cap adjustment screw and protective cap. All right, TXV cut in half, liquid in, the expansion out. The element or the head, the rod pushes the spring the element head rod pushes the spring. Okay, next slide. This is the external equalizer over here, suction liquid, the head goes over here. Strainers, this is about strainers. So there's this little filter that goes in the line. We have inline strainer, we have the screw-in type strainers. And that's the one brand new from the factory. And these overheated. One of them have acid, and here a little of acid erosion. And there, how you like that? This is going into the expansion valve, making it clog up. We have different kind of expansion valves. These are stainless steel. Stainless steel, 3 parts interchangeable. Look at that. You can, the body comes to the body, the head, and the spring and the. All right, and this one also you can replace the bottom part interchangeable orifice. Now the common TXV that come in a box, but sometimes at the HVAC store you call them, I want expansion valve. Come over, Robbie. We'll build it when you get here. They don't even build it until you arrive. They give you 3 parts. They give you a valve and 3 empty boxes. And the box is the element, the head is in one box, the body in one box, and the needle assembly in the other box. They put oil on top of the body and on they put oil on the body and screw in the head. And they put a tag to identify which cartridge it is in the valve. So next time I gotta replace the valve, they know. The body have number on it, the head have number on it. The only thing you cannot see is the cartridge inside. So they put the little tag on the cap tube on the transmission line. I never done it because we don't do it technicians, but people at the parts house, they do it all the time. Now, function of the let's go back to the external equalizer. Remember, we have the sensing valve transmission tube on the TXV and the suction and the transmission line. That's what's important. Now, saturated liquid starts. Saturated liquid ends, correct? At the end of boiling, superheated vapor right here. We have superheated vapor 10 degree. External equalizer will read the total pressure and adjust properly. That's why we have it, because we have 3 multi-evaporators. Suction line temperature minus boiling point equals superheat. In this case, it's 10 degree superheat. All right, now do not install an equalizer. What will happen? No equalizer line. Evaporator 1, it'll be not too much saturation. The freon will boil quick. The evaporator 2 in the middle, saturation will end over here, will add, and the bottom one will be flooded. Saturation ends 100%, barely. Okay, so now with external equalizer, all 3 are even. Without equalizer, temperatures, pressures are different in the evaporator. Superheat 55, superheat 40, and here superheat 0. Still saturated liquid. Pressure is gonna be erratic. Pressure temperature will change. TXV will not work. Superheat, who knows? Total superheat, who knows? Okay, enough of that. Now, low side, talk about how it should be. What happened when we have high superheat? What happened when we have low superheat? Normal superheat. The heat absorbing is normal. The XV normal, boiling 2010, 100% vapor towards the end of the evap. Perfect. Perfect. Latent heat is the thermal energy absorbed or released by a substance during a constant temperature phase change. I covered that in basic. Superheat. Now, that's your sensible heat, right? Sensible heat and your latent heat. Superheat is your sensible heat. Saturation liquid vapor mix is your latent heat. And it's normal because we are about 8 to 12. Same slide. Okay, so it should be, a superheat should be 8 to 12. Boiling point minus saturation temperature equals boiling point or saturation temperature minus suction line temperature, end of the evap, equals superheat. All right, now, what happened if latent superheat, TXV starving, 60% liquid, 40% vapor? We have very little latent heat, 100% vapor towards the middle. We have very high superheat, heat absorption very low. A starving TXV will restrict the flow of freon into the evap coil, right? Because maybe failing sensing valve, incorrect superheat setting, valve calibration, low refrigerant charge. Right now, superheat should be 8 to 12. Evaporator with very low superheat. All right, it's flooded. Evaporator is flooded. TXV when valve open too much. All right, 99% in, 1%, 99% liquid in, and 90%, 10% vapor. We have barely any superheat, right? Heat absorption is high. It is efficient, okay? And the causes are loose or improper mounting sensing bulb, correct. Sensing bulb is not there, right? Will sense false signal, will open more because sensing bulb is measuring high temperature. If it's overcharged, then the liquid in will cause it. That's for standard, not balanced port. If it's overcharged, also could do that. Loss of bulb charge, no. Loss of bulb charge, yes, correct. No pressure, same thing, will go up. High heat load or door left open also will do that too. Compressor will slug. And the whole idea of all this is to protect the compressor. We don't want slugging. All right, so that's how it should be. That's superheat high, superheat low. That's the best way to explain superheat is the temperature differential between the liquid vapor mist saturation temperature and the superheated vapor on exiting the evaporator. Next, expansion valve details. Temperature 40, 40, and 50 superheat. Between 40 and 40 is your saturation liquid vapor mix, latent heat, and 40 to 50 is your sensible heat or superheat also. So now the valve will adjust now the temperature at the end of the evaporator is 50 degrees. 50 degrees equals 84 pressure of the diaphragm. Diaphragm will push, adjust evaporator pressure, spring pressure. Adjusting superheat to lower, decrease superheat, decrease spring pressure, increase flow. To raise superheat, increase spring pressure, decrease refrigeration of the evaporator. It's very rare to adjust. Eliminate system and install errors first. System and install error, we're going to cover that next. Ready? It is very rare to adjust TXV. Installation error, if the bulb is not in contact with the tube. First, I'm sorry. The bulb placed in air curtain is not insulated. Bulb not firmly secured. Thermostatic expansion valve, external pressure equalizer not mounted. All these is sizing error, install error. This is high side, dirty string, low side problem errors. Okay, I mean, restriction errors, system errors. I'll tell a little story about the mountain winery. The only time I adjusted an expansion valve, so I've been in this business since 1994, out loud. I serviced over 1 million refrigeration in my life and air conditioning. Only once, because at the mountain winery, they do concerts, suction pressure low and the ice forming on the compressor, and the sticker was burnt. How do you like that? That's indication of overheating, bad installation, right? The guy did not, he overheated the valve. I have a balance port for emergencies with my truck, but with my luck, I'm out of oxygen. I cannot braze. I have to wait an hour because traffic one way going up to the concert venue. They have concerts there before a show. Half hour to town and about an hour and a half to the HVAC store, an hour, 2 hours back. What? It's ridiculous. So I adjusted it, had a nice dinner prepared by executive chef, watched the concert. Then we end up replacing the valve during the next PM and filter dryer. And of course, it was overcharged. Okay. It is very rare to adjust TXVs. But if you have to adjust them, you're gonna know how. So adjusting, they say clockwise, counterclockwise. It's confusing as is. Just how it works. Lefty loosey, righty tighty. That's how it works in almost everything. So if you wanna screw it in, it's gonna go up. Screw it out, it's gonna go down. Simple as that. All right. So back out to adjust. That means, and oh, I'm going too fast. Back out to adjust, and when you back out, we'll let more refrigerant in. Look at your liquid level went more liquid. Superheat adjustment. As you can see, you move it up, it will open more. You move it down, it will open more. Okay. I screw in. Excuse me. Okay. Adjusting 2 full turns will cause it to restrict. Liquid level is gonna be less. All right, enough of this. Now let's talk about heat pump. Enough adjusting heat pump TXVs. We have different TXVs for different styles. Heat pump TXV, the Danfoss TR6. It is for light commercial and air conditioning and heat pump system. It's designed for the new A2L alternative refrigerant, and it is with a built-in check valve. That's why it's a heat pump, and it's a balanced port design. And this is the Sporland version of it. traditional heat pump versus TXV and a built-in check valve. Traditional heat pump, traditional heat pump, this designed 2 check valve and 2. There we go. Traditional heat pump, you have 2 check valve and 2 TXVs for bi-flow for reverse. But the built-in check valve, you eliminate the check valves. Alrighty. We have TXV for freezer, the Z type and the ZP type. All right, the Z type is for low temperature. This is the charge of the head. When you see Z at the end, it typically significates cross ambient for low temperature walk-in coolers and freezers, typically 0 to 10. And now we know AA is for balanced port. Isn't that cool? So this is a AAZ, okay? Balanced port and for freezers. The Z is for walk-in freezers and coolers with solenoid valve pump down. This is important because we have the ZP type, which is ZP is a MOP, maximum operating pressure, all right? Maximum operating pressure is designated with Portland designation. It means it will automatically limit the maximum pressure in the evaporator. All right, it prevents motor from overheating by limiting pressure, preventing compressor motor from this after system pull down. ZP is for self-contained freezers without solenoid valve. Or that could be used on refrigeration too, but freezers. Pull down is when the freezer goes from very warm, from warm freezing temperature, from defrost, from cold, from warm to freezing after defrost. Alrighty. Now for this, okay, this one is the rapid pressure balance TXV, which what it does is it's built into, it's designed to quickly energize the high side into the low side during the off cycle. That's for air conditioners. Okay, so when the AC shuts off, you want the pressure to equalize. All right, now troubleshooting, failure to feed. If we have a shut off solenoid valve, make sure it's on. Make sure it's not overheating. Make sure the cap tube is not broken or pinched, or the transmission line. The valve have debris in it. Force the valve open. It says force clockwise, counterclockwise, blah, blah, blah. Then it says replace the valve with a new one. Like I said, it's very rare to adjust it. Replace the valve, inspect the old one for debris inside. Cannot adjust superheat. Make sure sensing valve is good contact. Adjusting superheat, 1 full turn, wait 5 minutes. If the valve is unsecure, increase superheat, wait 5 minutes. It's a pain in the butt to replace it, adjusted it. Flooding the evaporator, the poor superheat adjustment valve replacement installation. It's caused by poor superheat adjustment or valve. I mean, somebody messed with the spring. Somebody messed with it, okay? For proper airflow across the evaporator, make sure it's not dirty, proper airflow. Sensing valves mounted properly, and increase the eighth of the turn until significant superheat happens. Suction line too warm, check for proper system subcooling. Check for obstructed line in the liquid. Try adjusting superheat. Alrighty. It is very rare to adjust. Next, we have a single evaporator controlled by 2 expansion valves. All right, now we have A and B, red and blue. And then if we want 50% compressor running 50%, we'll open the A valve, close the B valve, and that will leave us 75% capacity. This is very rare. I just figured I'd mention it because it's really cool. I never seen 2 expansion valves controlling 1 evaporator, but you learn something new every day. That's why HVAC is so cool. Alrighty, enough of this. This is visible faults. Next, we're gonna do some pictures. Alrighty, so over here, the metal strap have more surface area, better heat transfer. Do not put Ziploc ties. Metal strap only. Plastic is not a good heat transfer. The liquid line filter dryer should be next to the service valve. It's the wrong location of the filter dryer here. Do not install upside down because liquid from the bulb will never expand the diaphragm. Oil may leak around the push rod and fill the space underneath the elements. Never install upside down. Next, restriction on the filter dryer. The blue, all these are restrictions, alrighty? But this one, it looks like restriction, but it's not. This is system and recovery, the red. Liquid refrigerant, the oil, and liquid refrigerant in the oil boiling off during recovery. This is a clue I have because I can see frosty up here on top, frosty at the bottom, colder on the bottom. That's how this is in here, like a little tiny P-trap. Oil is vapor not. This is not restriction. System is not running. This is recovery. These are restrictions because you can see ice after the filter dryer, which we're not supposed to see ice on the filter dryer. All right, restriction on the filter dryer. The pressure will drop. We cannot measure the pressure, but we can know by temperature change. Okay. And so many times people tell me it's bad TXV, but it's actually bad filter dryer. All right, now, any issues? This one, no issues. There's 3 clues. The one on the red have issues. A walk-in freezer evaporator about to go into defrost. I can tell so much just by visual inspection. The TXV body is clear. Alrighty. Number 2, the expansion at the distributor. Expansion correct at the expansion line. And number 3, even ice formation everywhere. That will tell me it's about to go into defrost. Nothing's wrong with it. This one is low in Freon. Why? Because walk-in cooler is not shining off because low in Freon and ice top 3/4 way. Clear, top third, ice. The ice is built up. The ice built up on the suction line, not because suction line is frozen, because the ice from the evaporator is freezing the suction line. Right? The suction line is not frozen from the inside because it's above 32 degrees. There's no ice on top. Suction line at the end of the evaporator. It is frozen just because the cold from the ice is making the suction line frozen. Next, ice on the compressor body. Ice even everywhere. Airflow issues. Nothing's wrong with the metering device. This one doesn't. Both these are orifices, huh? Yeah, both these are orifice. Okay. This is airflow issue. Ice is even everywhere. Now, there's your restricted expansion valve already. Expansion inside the valve. Expansion should be after the body. Alrighty. On the red, liquid slug on the compressor. This is slugging in the middle. The one of the blue slugging because the bottom picture, if you remember a compressor, the head not supposed to be in freezers. We can have the whole body iced up. It's fine as long as no ice on the head. You see ice on the head, that means we have liquid slug back. Give it maybe 1 day will last, or maybe a year, maybe 10 years, but I guarantee you it's going to fail. And not 10 years, but it will fail. I guarantee you. If you see this, it's bad. No ice should be on the head of the low side. All right, now, restriction. Expansion should be at the evaporator. This one. All right, now, this is a little tricky now. Is it restricted or low in Freon? It's low in Freon. Because it's iced up only at the bottom. The expansion line is so cold, it's iced up. Lower pressure equals lower temperature. Now, the ice from the expansion line is frosting the body, okay? The body is not frosty because it's restricted. The body is frosty because the expansion line is so damn cold. Makes sense? It is low in Freon, no restriction here. Okay, I hope you guys get this. Now, correct ball position depends on the size of the pipe. Alrighty. Because oil goes at the bottom and you don't want to put it at the bottom like this. Is bad. This is, it's barely contacting here because next to a joint connection. And look at this, joint. You can tell hillbilly, and it's gonna leak here. Liquid line touching, very nice. Alrighty. The oil return at the bottom. Next, do not place the bulb on the joint bend. Transmission tube should never go down, because if it goes down, the liquid will go to the head of the diaphragm, and the diaphragm will not work properly. The cap tube should be pointed upward, so transmission line. The best option is this way, but sometimes you don't have a chance. Sometimes, especially on walk-in coolers, you don't have room to put it. Alrighty. Next, always make sure you use a wet rag is the best option. You can use the wet rag chemical, but it's costly, time consuming. And if you don't apply it properly, you overheat and you have issues. But it looks cool. I tried it once, and only once, and never again. Use wet rag if it's free and works good, guarantee no issue. As long as the rag under 112 degrees, guaranteed. As long as the rag is wet, we know it's not gonna overheat. Okay, it can reach temperature up to 250. So, okay, cool, makes sense. Wet rag is the best option. Now, do not use Teflon tape. This is from the Danfoss Learning. Teflon tape will fill up the thread, preventing normal friction of flare nut. Do not over tighten, because if you over tighten, you could mess. And you can see here, and the Teflon tape could go inside, damage. No need Teflon tape on a compression. All right, now, a free education from Danfoss. Welcome to Danfoss Learning. Question 1. The TXV controls temperature of the evaporator, and it's false. It controls the pressure. What is the most correct sequence event to the temperature of the sensor bulb increases pressure of the refrigerant charged in the bulb, forcing the TXV to open. Correct. The expansion valve sensing bulb must never be mounted on the bottom of a horizontal suction line. Why? We just studied that. Because any oil present in the line will be on the bottom of the tube, may interfere with the bulb's ability. Alrighty, the sensing bulb should never be mounted next to a large mass, because the component will affect the radiating temperature. Right, now, the bulb must be installed if exposed to air. Yes. And this one, before attempt to adjust superheat, conditions to check to ensure system is not under pulled down or coming out of defrost. Correct. Right, now, if the evaporator is dirty or the airflow across, what will happen? Temperature, pressure, refrigerant to the environment. Okay, so evaporator is dirty or bad airflow, what will happen, right? Temperature, pressure will increase, go up. Temperature will increase and pressure remains constant. No, it doesn't sound right. That both go hand in hand. Temperature and pressure will act opposite of each other. No, temperature and pressure will decrease. Correct. There we go. All right, next. This is one I got wrong. No, the next one I got wrong. If a TXV is not feeding into the evaporator, what's the correct procedure? If the TXV is not feeding into the evaporator, what is the correct procedure to initiate? Add refrigerant until the FV starts. Check upstream obstruction. Check ensure sensing bulb. Inspect valve. Adjust superheat. Try to force the valve. So all these are correct. I actually got this question wrong. I did not pick the last one. Okay, I figured we should not. I didn't think about debris inside. I didn't read the question right. I was tired, I guess. I got this question wrong because I did not think of it plugged debris. You gotta pay attention when reading questions. How can I be plugged? I guess it can from the previous slide. If we have acid, the strainer will get destroyed, right? And then we could have caused debris. It is rare. I think it happened only once. I got 90% already. Now let's move on to the electronic expansion valves. Electronic expansion valve versus thermostatic. They both have information, right? Information, the sensing bulb is the information for the temperature. Information is a temperature probe. The pressure transducer is the information for the electronic valve. The external equalizer, I guess that suction pressure is the information. And we have spring is the control, and we have a control module. We have another control is the motor also. And they both have needle and, okay. Now this is expansion valve. We have the motor section. We have the body and needle valve. And we have pressure in and out, high pressure, low pressure. And separate, another example, the motor, the valve. This is an example of so many different kind of valves. I mean, so many options we can put into it. Backup power, computerized. It's called superheat controller. All right, now this is what I found online, electronic expansion valves. 1, 2, 3, 4 is the connections for the motor, for this separate motor. This is solenoid valve and alarm connection in case you have solenoid valve. It's optional. We don't usually have solenoid valve on EEV because the electronic expansion valve is used as a solenoid valve for pump down. And down here is the primary volt connection, 120 volt, 220 for North America, because it says 230 volt. I'm thinking, we don't have 230 volt. That must be Europe. And secondary is 24. It says 230, that's for Europe and the rest of the world, and 50 frequency. America is 60 frequency. Transformer depends on the size, 20 VA transformer or 40 VA. If it's, you gotta know what transformer to put. VA is voltage times amp of the secondary. I explained all this in the transformer video I made earlier. They say ground, we say earthing. That's the difference between Europe and us. Okay. Anyway, let's move on with this now. Now we have, it's so cool, suction line temperature goes in here. Evaporator pressure. And number 8 and 9, the pressure transducer and the temperature. There we go. Pressure and temperature 1 and 2, and 3 and 4 extras. I guess if you have 2 evaporators controlled by one module, maybe. Then a digital input 1 in. A digital inputs some controller. All these is to the other buttons for other controls. All right, enough of this. So this is the blue section, the red section. And now we have special new ETS Coley Bright by Denfos. It's a balance gauge assembly. It's a solenoid tight solenoid with sealed. It's a direct driven slider, stepper motor, laser welded joints, bimetal connection, stainless steel body, and side glass with moisture indicator. Alrighty, and there it goes. So now for a heat pump system, you only need one now. It does both ways. Okay, you will have a bi-flow heat pump, the compressor, the controller, 4-way valve, and temperature sensor, evaporator or condenser, and evaporator or condenser. So now only one valve does both. How you like that? Alrighty. Do not install upside down. Always use wet rag over 120, 257 degree. Okay. This is also another one I saw. We have the line goes in, normally open, normally close the switch. This is for heat pump, 4-way reversing valve. Compressor on off. 5-wire or 6-wire for the motor. This is for the separate motor. Communication, discharge temperature, condensing temperature. Two temperatures, one on the discharge line, one on the liquid line. And we have this is the screen up and down, left and right, and evaporator temperature, and suction line temperature, both. One sensor inside the evaporator to measure about 1/3 into the evaporator, or 2/3 out, excuse me. That's probably for freezers, and suction line temperature. Then pressure sensor and another extra pressure sensors. And communication port number 10. Alrighty, enough of pretty much same thing. This is another one. Sensor, temperature, pressure, temperature, and valve. All right. End of metering devices. Thank you very much. Have a good day. Peace, love, peace, and happiness. Anybody have any questions? Let me know.